Assalamualaikum and a very good afternoon. My name is Munir Afnan bin Mukhtar. I'm from University Malaysia Pahang. Today I'll be presenting my research with the title of Thermodynamic Analysis of a Gamma Configuration Stirling Engine. Today, with the growing number of world population, worldwide demand for energy are also drastically increasing. As reported by the US Energy Information Administration, the world energy consumption is estimated to rise up to nearly 50% between 2018 and 2050. So this situation will be more worried with the limited of non-renewable resources as the main energy supply resource. There is also increasing in environmental problems like increase in greenhouse gas emission, since the conventional power generators are based on fossil fuels energy conversion. Thus, with the growing awareness of the shortage of the fossil fuel resources, researchers tend to focus their research on developing one of the most effective energy conversion systems, which is Stirling engine. Stirling engine is a heat engine that uses any external heat sources in converting heat energy such as solar energy, biomass, and geothermal into useful mechanical energy. This special characteristic of Stirling engine has made it a potential future green engine. Other than that, Stirling engine also possesses other advantages like low noise production, high efficiency, less air pollutant, easy maintenance, and low vibration. So due to its promising alternative solution in producing clean energy, it has hold intentions of developers and researchers towards Stirling engine recently, and efforts have been done worldwide in developing Stirling engine for the future application, including numerical analysis and prototype development. Typically, kinematic Stirling engines are categorized into three main configurations, which is alpha, beta, and gamma. All of them have similar thermodynamic cycle, but only differ in their mechanical characteristic. Researchers found that only gamma-type Stirling engines are suitable for low temperature difference application. So, according to Tombarek and Verma, the development of Stirling engine that works with low temperature difference has the potential to be more attractive in the future since the application is wider. Therefore, researchers have focused more on developing gamma-configured Stirling engine, including the authors. Prior to the prototype development of gamma configuration Stirling engine, the geometrical parameters of proposed design need to be verified in terms of its workability. Therefore, the objective of this study is to run a simple thermodynamic analysis on the proposed design of gamma configuration Stirling engine in predicting and verifying the working condition of the proposed engine design. The thermodynamic analysis is done by adapting a modified model of Schmidt theory. The analysis model was based on adiabatic model in which the engine was split into three working spaces, which are expansion space, regenerator, and compression space. So the assumption made in applying Schmidt analysis are listed as follows, which is the first one is the working fluid obeys the ideal gas law, and then the engine is perfectly sealed and there is no working fluid leakage. Thus, the total mass of the working fluid is constant. The temperature in each working space is known and there are no temperature gradients in each working space. The engine is running at a constant speed, and then uniform instantaneous pressure in the working space, and the last one is the displacer and power piston are moving in a pure sinusoidal motion. So this is the flow chart of the analysis. The process is started with defining the engine geometrical and operational parameters. So this is the illustration of the engine, and then the details of the geometrical parameters can be seen as listed in the table here. The analysis is done with the initial condition of power piston at the bottom dead center, and it is presumed that the engine is running at a constant speed of 300 rpm with reference to the typical minimum speed of kinematic Stirling engine. It is also said that the engine is running at atmospheric pressure with air as the working fluid, and the expansion and compression temperature is 573 Kelvin and 300 Kelvin respectively. And also the phase angle was set as 90 degree. Then the reciprocating displacement of displacer and power piston from the RTDC is determined by using equation 1 and 2. This equation were derived based on engine geometry and trigonometry rules. Theta is defined as the crank angle measured from the engine vertical direction and rotating in clockwise direction. Meanwhile, alpha is the phase angle difference between displacer and power piston. The swept volume for displacer and power piston can be determined in terms of YD and YP and their respective cross-sectional area of displacer and power piston. The expression of the swept volume are as follows in equation 3 and 4. The last one, the total expansion and compression space of the Stirling engine can be calculated by summing together the working space swept volume with their clearance and dead volume. By applying the ideal gas equation of state, the initial total maximum working fluid mass M can be calculated by taking the initial condition of pressure, volume, and temperature. As stated in the assumption before, the total mass of the working fluid is constant, which gives the expression as in equation 8. And then from the ideal gas equation of state, the change in mass due to the change in pressure of expansion, regenerator, and compression space are found in the equation 9. So when we substituting the equation 9 to 8, it gives uh, the expression as in equation 10. And then it is assumed that the pressure to be uniform throughout the working space. So we rearranging the equation 10, and then it gives equation 11, which is in terms of P. Then the equation of instantaneous working fluid mass in each working space can be written as listed in equation 12, 13, and 14. And then since the analysis is conducted using ideal adiabatic model and only considering three working spaces, which is expansion, regenerator, and compression space, the energy evaluation will only consider the total indicated work of the engine. So the equation would be as stated in the equation 17. The graph shows the reciprocating displacement of the spacer in a power piston from the anti-DC position. The initial positioning of the power piston is said to be at the VDC of the cylinder, which gives the maximum displacement of 0.061 meter, is equivalent to its stroke time. The displacer also shares the same value with the power piston, since both of them have the same value of crank offset radius and connecting rod length. During the engine cycle, it can be seen that the displacer is leading the power piston with 90-degree phase angle. This is to allow the displacer to displace the working fluid, traversing back and forth between the expansion and compression space during the engine running. The selection of the phase angle also is very important in determining the volume variation in the engine cycle that at the end affects the engine performance. The graph represents the engine volumetric displacement of expansion and compression space of the engine and its cyclic pressure. As the power piston and displacer moving upward toward the TDC, the volume in compression space is increased while the volume in expansion space is decreased. The increased volume of compression space is due to the increasing clearance volume at the bottom of the displacer is more rapid than the reduction volume in the power piston cylinder. So the total maximum working volume is seen to be at the beginning and at the end of the cycle, while the minimum total working volume is in the middle of the engine cycle, which is at 180-degree current angle. On the same graph also, the working fluid cyclic pressure is plotted in determining its relation towards the working space volume variation. The cyclic pressure is varying from 109 kPa to 199 kPa throughout the cycle. As can be seen, the maximum pressure is achieved when the total engine volume is at its minimum value and vice versa. Therefore, the total engine volume variation, which is derived from the reciprocating displacement of the displacer and power piston, plays an important role in determining the engine cycle pressure. The mass of the working fluid as a function of the crank angle also being plotted. It can be seen that the mass curve of working fluid in compression space almost mirrors the expansion curve. This indicates that the working fluid alternately enters and leaves the compression and expansion space response to the reciprocating movement of the displacer and power piston. So the compression space exhibits a maximum amount of working fluid in early cycle. This means that the engine is experiencing a compression process during this phase. The same situation also occurs in expansion space. The maximum working fluid in expansion space is at the half end of the cycle, which means that the expansion process takes place at the half end of the cycle. Meanwhile, the PV diagram for the expansion and compression space of the proposed engine is presented in this graph. The area enclosed by the expansion curve and compression curve illustrate the positive work done and negative work done produced, respectively. However, the area enclosed by the PV diagram represents the net work done of the system. With the assumed speed of the engine is 300 rpm and the net work done produced, it is calculated that the net indicated power produced is 33.41 watt. It is mentioned earlier that the choice of the phase angle does affect directly the engine volume variation, thus the engine performance. Therefore, range of phase angle from 70 degree to 120 degree are selected in determining the most effective phase angle. So the PV diagrams were plotted. From the calculation, the highest power output produced by the engine is when the phase angle at 90 degree. This shows that the selection of 90 degree phase angle for the engine design is a right decision. In this work, a simple thermodynamic analysis has been conducted on a proposed slider crank gamma configuration Stirling engine. By adopting a modified Schmidt ideal adiabatic model with air as the working fluid, 573 Kelvin of expansion temperature and 300 Kelvin of compression space temperature, run at atmospheric pressure and at 300 rpm of speed, the engine is predicted to produce 33.41 watt of power. The selection of 90 degree phase angle is verified as an effective phase angle. Therefore, the study showed that the proposed design can be carried out for the development of the Stirling engine prototype. So that's all from me. Thank you.